So in this video, we're going to talk about the fluid statics. So here, consider a small rectangular element of the fluid. And also note that there are two different types of forces in general. The first one is the surface forces, and the second one is the body forces. The surface forces are, for example, the forces due to the pressure, which acts on the surface of the element, and the body forces are the forces that are acting on the volume of the element, like the force due to the weight of the fluid within an element. So if we take a look at this element in the YZ plane, then this will be our element. And here it's the center of the element. So one of the forces that we have at the center of the element is the body force due to the weight of the fluid within that element, which is equal to gamma of the fluid times the volume of the element. So here the gamma has a dimension of Newton over cubic meter, which is the specific weight of the fluid within that element. And here this term is the volume of the element, which has the dimension of cubic meter. So the resultant force obviously has a dimension of Newton. Then for the pressure distribution, we assume that at the center of the element, the pressure is P. So the pressure acting on this surface on the right side of the element, which is the pressure acting on this surface, will be equal to. So we assume that the pressure at the center of the element is P. So here from the center of the element, and this is delta Y, we are moving to the right, which is the positive direction of Y, and we travel delta Y, half of delta Y. So the value of pressure, since we're moving in the positive direction of Y, will be plus the distance that we're moving, half of delta Y, times the pressure change as we move. So the change in pressure as we're moving in the Y direction. So this will be the pressure distribution on this surface here. And the resultant force will be the pressure distribution times the area of the surface, which is delta X times delta Z. So again here, we have pressure, which has a dimension of Newton over squared meter. And here's the area of the surface, which has a dimension of squared meter. So the resultant force, again, obviously has the dimension of Newton. And similarly, we can write it for the surface, the left surface of this element, which is this area. And again, as you can see, we have P, the pressure at the center of the element. And here we have the negative sign because we're moving to the left, which is in the negative direction of Y. Then we have this term, which delta Y over 2 is the distance that we're traveling, we're moving. And also del P over del Y is the change in pressure as we move in the Y direction. And again, del X del Z is the area of this surface. So then we can write the Newton's second law for this element. And if we write the Newton's second law, here the force is a vector which has three different components in X direction, Y direction, and Z direction. So for example, if we want to write it in the Y direction, so as we have in the first slide, here is the Y direction, X direction, and the positive Z direction. So these two forces are the forces that we have in the Y direction. This one is acting in the positive y direction, so it's positive, and the other one is acting in the negative y direction, so it has a minus sign, negative sign. And by expanding this, we will find that the value of the surface force, remember that it's the surface force, since we only have the effect of the pressure. So this is the surface force in the y direction, and similarly we can find it for x and z direction. So here are the forces in three different directions. So this one is the surface force that is due to the pressure. And also we have a volume force here, which is due to the weight of the fluid within that element. And the body force here is given. So we can write the Newton's second law for this element. So F is equal to the mass within that element, mass of fluid within that element, times the acceleration of the element. So as we saw, the force is the surface forces and also the body force here, which is equal to the mass times the acceleration. So we rewrite it here. But what is mass? The mass of the fluid within that element is defined as the density of the fluid times the volume of the fluid. So here rho is the density of the fluid within that element. And here the delta x, delta y, and delta z is the volume of the fluid. And again, here rho has a dimension of kilogram over cubic meter, which is for the fluid. And if we multiply that by the volume of the element, obviously the unit will be kilogram, which is for mass. So if we substitute the value of mass, this equation, into here, we can find this equation for the Newton's second law. And in here, as you can see, that we can divide all the terms by the volume of the element. So these terms are canceled. So it can be summarized and written in this form. Also here we can define an operator, which we call it nabla. It's a vector that has the change of any property in x direction, then the change of it in y direction, and its change in the z direction. So as you can see here, we have it del over del x, del over del y, and del over del z. So we can write the equation as minus the gradient of the pressure minus gamma in the k direction is equal to the density times the acceleration of the element. So we can say that for a fluid element in which there are no shear stresses, the general form of pressure is given as this function, which we have derived it using Newton's second law. And also for a fluid at rest, we know that the acceleration will be equal to 0. So here the acceleration is equal to 0, and minus nabla p minus gamma in the k direction is equal to 0. Then if we again expand the operator here, we will find this equation, which the 0 here is actually 0i plus 0j plus 0k. So we can write that for the x direction, these two are equal. Then for the y direction, these two are equal. And for the z direction, this term is equal to this term. So from here, we can find that del p over del x is 0, del p over del y is 0, and del p over del z is minus gamma. So since del p over del x is 0, it means that the change in pressure is independent of x. And also since del p over del y is also 0, so the pressure is not a function of y. So we can find that the pressure is only a function of Z. So since the pressure is only a function of Z, here del P over del Z can be written as the total derivative, which is dP over dZ. So from the Newton's second law, we found that dP over dZ is equal to minus gamma. And also for incompressible fluid, gamma will be constant. We know that the gamma, which is the specific weight, is equal to the density of the fluid. Gamma of any fluid is the density of the fluid times the gravity. So for incompressible fluid, gamma will be constant. And here we can move the dz to the right-hand side of the equation. So dp will be equal to minus gamma dz, and we can integrate this equation. So the integration between 2 points, P1 and P2, and here it's between those same 2 points, and since gamma is constant, we can take it out of the integration. So here this will be the equation that we have, and by solving the integration, we can find that P2 minus P1 is equal to minus gamma times Z2 minus Z1. And this type of pressure distribution is commonly called hydrostatic distribution. Static, since the acceleration is zero and the fluid is at rest. So also we can write it in a different form. So we can write that Z2 minus Z1 is the pressure difference divided by gamma, and we can call Z2 minus Z1 as H. So H will be equal to P1 minus P2 divided by gamma, where H is called the pressure head. And this can be interpreted as the height of a column of fluid of a specific weight, which is required to give us the pressure difference P1 minus P2. So the equation that we can find from here is known as the Manometry equation, which is commonly used in fluid mechanics. And it relates the pressure value at two different points. And as we found, the pressure is equal to gamma times H. So the pressure in fluids at rest is only a function of gamma and H, where gamma is equal to rho times G. So the pressure is only for fluid at rest without any shear stresses is only a function of the fluid rho and also the elevation H. So whenever the fluid changes, the value of pressure will change, and also whenever the elevation changes or we move, the depth changes, the pressure will change as well. And also the value of H is measured with respect to an arbitrary reference line that we can put a reference line wherever we want.